So welcome to the second week of the course, this hyperspectral and microwave remote sensing for geological applications. Last week we have discussed on hyperspectral remote sensing. Three of the faculty members took lectures and deliberated on these techniques, data processing, and geological applications. And in this week, we'll discuss essentially on microwave radar remote sensing for geological applications. So at the end, that is the last day, we'll discuss on how this hyperspectral remote sensing and microwave remote sensing individually can be used for geological applications and in combination, in synergy. What is the strength of both these techniques together for geological applications? That we will discuss on the last day. So for today, it is an overview of microwave radar remote sensing for geological applications. And myself, R.S. Chatterjee from Geosciences Department. I am also your course director, and Mrs. Richa U. Sharma is the course coordinator, you know that. So today's lecture, microwave radar remote sensing for geological applications. You know, this what is microwave remote sensing, first of all? It is the remote sensing in the microwave region of the electromagnetic spectrum. Two broad groups of microwave remote sensing. One is passive and another is active microwave remote sensing. In passive microwave remote sensing, it is similar to your optical or thermal remote sensing. Okay, essentially it is similar to thermal remote sensing. It senses microwave radiation which is emitted from the earth, and the sensor is known as the radiometer. So radiometer senses microwave radiation which is emitted from the earth, and based on this electromagnetic radiation, it can characterize the object. Okay, that is passive. And active, which is more important, in this case, this your radiation, it comes from the sensor itself. So it illuminates the target artificially, and then these electromagnetic pulses, essentially in the microwave region, it is transmitted from this antenna, which is a radar antenna, and then this electromagnetic pulse, it reaches the earth surface. It interacts with the earth materials depending on your material type, it is material geophysical properties, and after this interaction it comes back and it receives that. So this active microwave remote sensing, again, it has two broad types. One is imaging, that means every these points within this swath, similar to optical or this thermal, this remote sensing techniques, you have the full image. Okay, this is imaging, the active microwave remote sensing, and this is basically radar. And the radar, you know, this is the acronym of radio detection and ranging. So this is basically a ranging device. So ranging with respect to the distance and the time. So time is important to sense the target. And in imaging radar, there are again two types. Okay, two branches rather. One is real aperture radar. Previously, we used to work with the real aperture radar, which is also known as side-looking airborne radar, because this real aperture radar was not possible in the satellite-based platform. Why? Because if your height of the platform is very high, in the hundreds of kilometers, then the resolution will be in kilometers. Okay, and that is not very much useful for our remote sensing purposes. So that is why this height should be optimum, and in case of airborne platform only, it was used real aperture radar. So it is side-looking airborne radar. And then came this your synthetic aperture radar. So this we'll discuss on that, the synthetic aperture radar mostly. And on the other side of the remote sensing is a non-imaging radar. That is the altimeter, the scatterometer. Altimeter is used for this ocean surface height measurement. It can also be designed for the terrain height. but these are not these for the entire swath. It is beam based. And scatterometer, again, it is for the wind, this direction mapping of the ocean surface, and it gives you the scattering coefficient, scatterometer. And you don't have this entire swath image for this, because these are not imaging radar, they are non-imaging radar. Now you see here, this is how this active microwave remote sensing work. So you see, this is the satellite, and here this radar antenna is placed, and then this, you can see very clearly that a red color, this is the pulse, or it is the transmitted pulse, which is coming from the radar or transmitting this antenna, and it is coming, how it is radially. It is radially moving, and it is finally reaching the Earth's surface. But because it is transmitted radially, so it reaches the Earth's surface at different times, because the distances are different. And so you are getting many yellow colored this return signal. So by sending one transmitted pulse, we receive a number of many your return pulse. Okay, so radar is an active illumination system that sends out electromagnetic pulses to the ground radially, and this, after this interaction with the Earth surface, the backscatter radar signal is received essentially after a fraction of a second. It's a very short time it takes, and then this receiving antenna, which is co-located, okay, very close to the transmitting antenna, it receives this pulse, and based on that, this return pulse, as it is received with respect to different times, this entire Earth surface is imaged. Okay, this is how this imaging radar works. Now we see this radar remote sensing. There may be some disadvantages as well, but there are many advantages in this active microwave, this radar remote sensing. First of all, you know, this is active microwave instrument, isn't it? So this is active remote sensing. So you can transmit anytime when the satellite is orbiting the Earth's surface. This pulse can be, electromagnetic radiation can be transmitted, and it can be sensed. So anytime it is possible, essentially the day and night imaging capability it has got. And most important factor here, you see, it has a very long wavelength. It is a longer wavelength, means in case of optical remote sensing, you have seen what is the visible, this remote sensing wave. The wavelength of radar and the wavelength of this optical, this remote sensing, it is going to be 10 to the power 4 or even more times. So this very long wavelength in case of radar gives you many advantages. So it is an unique property because of the long wavelength. So because of that, it can penetrate through the atmosphere, and it can penetrate through even dense vegetation. That means in case of forest, it can penetrate through this, and sometimes it can penetrate through ground also. Although it cannot penetrate for hundreds of meters, only few meters it can penetrate, but it penetrates, and it can give you this near surface features from this your longer wavelength radar imaging. And this next property is it is side looking. It's side looking imaging, and it provides data across flight directions. And that is why it is highly sensitive to topographic elevation. And when it is sensitive to topographic elevation, it highlights your physiographic features. It highlights geomorphology, it highlights geological structures. So the side-looking imaging has certain advantage for highlighting the geological features. And the other point is, this is imaging by coherent microwave radiation. It is a coherent signal because you are transmitting from the antenna. You know the source of the electromagnetic radiation. So this is a coherent signal, whereas in case of optical remote sensing, the sun is the source, and there are many radiations. Millions of radiations are reaching the Earth's surface. Millions of radiation is reaching these pixels. So this is not coherent. This is a non-coherent in optical remote sensing, whereas in case of radar remote sensing, it is coherent, so it can be tracked, and so there is phase, and the polarization has a lot of value in case of radar remote sensing, particularly the phase, okay, and also polarization of this electromagnetic radiation which is transmitted and which is received by the radar. So this is very helpful for characterization of the targets, because it gives high precision measurements in terms of haze and in terms of polarization. So that we will discuss in the coming lectures. So see, this is the illustration. This is the illustration of the how it this electromagnetic radiation it is going through the atmosphere. You see, for the entire electromagnetic region, starting from your gamma ray or X-ray, then ultraviolet, visible, then near infrared, mid infrared, far infrared, all these together. Okay. Then comes your microwave. Okay. So here you see that this entire electromagnetic spectrum, there are some windows where this atmospheric transmittance is very close to 100%, and where we designed your sensors so that the electromagnetic radiation from the Earth's surface it can reach the satellite. Okay. But there are many regions where it is completely blocked by the atmospheric gases and the aerosol particles, particularly the atmospheric gases like water vapor, like ozone, like carbon dioxide. But if you see in case of a microwave, so neither your atmospheric gases or the aerosol, that is these dust particles, it cannot stop this microwave radiation. So here this atmospheric transmittance is very close to 100%. It's not absolutely 100%, but it is very close to 100%. So it can penetrate atmosphere at any time, even during the rainy season. It can penetrate through that, which is very, very important during rainy season, because you don't have cloud-free data in case of this optical remote sensing. But in microwave, we can have cloud-free data. Okay, so now see this radar imaging geometry. This looks, how radar looks, it looks this sidewise and off nadir, isn't it? But why radar looks, why it needs to look laterally, why it needs to look sidewise and off nadir? Why not vertically down? Why not nadir looking? See, if it was nadir looking, there was some problems. What kind of problems? There is some ambiguity, because you know this radar is a ranging device and it images on the basis of the time. When this radar signal, return signal is received, it will be imaged at that time. See it? And this time is a function of the distance. So if the distance of two targets is same, the return signal will reach the receiving antenna at the same time. And it won't be able to resolve whether it is coming from this point A and A dash. Okay, so there are 2 points, A and A. This is not the same. You can consider it B. So there are from these 2 points, the distance from your antenna is same. If it looks vertically, if it looks nadir looking, okay. This distance, both the distance are same, so the return signal will reach at the same time. So it won't be able to resolve the return signal from these 2 targets. Whereas if it looks laterally, sidewise, then you see these are the points over this swath, A, B, C, D, E, F. Okay, these are the points. Now all the points have different distance from the antenna. As the distance is different, time to reach this point and this return signal to come back from this point will be different. So because the time TA, TB, TC, TD, TE, and TA, they are not same. They are all different. As the time it takes to reach this target and to come back to the antenna is different, so it will image at different times. And all the targets can be easily resolved. All the targets can be resolved. That is why radar must look sidewise and laterally. It should not look vertically, nadir looking. In that case, there will be ambiguity and you won't be able to resolve these 2 targets on either side of this nadir, because the distances will be the same exactly. And this is when the terrain is flat. But when the terrain is sloping, there is a different scenario that we'll discuss in the slides to come. Now we see in the radar imaging geometry and the optical imaging system. The optical imaging system, I believe all of you know to a great extent. And optical imaging system, basically it is an angular system. And here, how to resolve these 2 targets, whether these 2 targets can be resolved or not, it is basically governed by their angular difference between these two. Okay. So if this angle is sufficient, then these two targets B and C can be resolved. And you see here how this B, C, A are imaged. B and C are imaged. B and C are just on the opposite sides. Just on the opposite sides. Through the lens. And it is passing. This is the imaging plane. This is the imaging plane. This is the ground surface. This is the ground surface. And this is the lens and imaging plane. Here the detectors are placed. Here the detectors are placed. So B is imaged here. So B is imaged here. And B and C can be resolved if this angle is sufficient. But in case of radar, it is not an angular system. It is a radial system. Why? Because this is the center of this circle, if you consider, and this is the radius. Okay, changing radius, the pulse is moving, and then pulse is reaching this point A, and in the beam direction at A dash, and then it is reaching on the ground at B, and along the beam direction at B dash, similarly at C dash. Now, whether this B dash and C dash you can resolve, it depends on what is the radial distance between these two. Okay, so this distance is important, and how it can be resolved, that we will discuss. That depends on this resolution in this particular direction. This is basically the range direction. Okay, this is the range direction along which the radar beam is transmitted. Now see the radar imaging geometry. So here this is the satellite, and this is in this direction the radar beam is transmitted, and radar beam is swath is from this to this. This entire area is imaged, but this area it does not image. So exactly in this the point at the nadir or for some distance, it does not image. It starts imaging from here, and this point is the near range point. And this distance from the antenna on the ground, this distance is near range distance, and the furthest point of the swath and from the antenna is this is the far range. And this angle of this radar beam with respect to the perpendicular, this angle is known as the look angle, whereas the angle with respect to the horizontal is known as the depression angle. Okay, so here you see the radar beam direction is known as the range or slant range direction. Okay, so along this slant range direction is how this your points on the ground is projected. So that distance is important for resolving these targets. So the distance on the radar beam direction, the projected distance, this among different points on the ground, so that is important for resolving these targets. And this is slant range, that is the radar beam direction, along which the ground objects are projected. Whereas on the ground from this nearest point of the swath to the furthest point, this line or this distance is known as the ground range distance. So these are some of the terminology. Those are very, very important to understand this radar imaging, your characteristics. Now let us discuss very briefly about some of the advantages of this radar remote sensing, because you know this radar is an active sensor, active microwave instrument, or AMI, so it has certain advantages. So these advantages, like this microwave radar operates both during day and night time because it is an active sensing device. So it is particularly useful for the polar regions, because a couple of months in the polar regions there is no sunlight, isn't it? It is night only, dark. So in polar regions, sensing it is very, very important. Optical remote sensing cannot image this during this period. The other advantages you see, it can penetrate through clouds and to a high degree through rain as well. So in the equatorial regions, you know, particularly in your tropical regions, there are a number of these rainy your months. So during that time, the cloud-free images are very, very difficult to get. So, but during that time, there is a problem of flood, and there is a problem of landslide in the mountainous regions, and you need image of during that time of hazard very desperately. But in optical remote sensing, many a times you will not get any image because it is cloud covered. So during that time, this microwave remote sensing is very, very helpful. It gives you this image because it can penetrate easily through the cloud. Also, microwave can penetrate through your smoke, dust, and ash. So it is useful for volcano mapping and volcanic hazard monitoring, although it is not very important for this our country because we have only one this volcano. It is sometimes active, sometimes dormant, that is in Barren Island. And this volcanic hazards is not a problem for us, but in many countries it is a genuine problem. So they need this microwave, this imaging is very, very important for them, particularly for monitoring of the volcanic hazards. For example, this your volcanic mud flow or lahar, okay, and during the volcanic eruption. These images are very much important, but optical remote sensing cannot give you these images. And this next point is it can penetrate through vegetation and also ground. So particularly in case of forest and where the forest is closed or dense forest, in optical remote sensing we get the image of the forest canopy, that is top of the vegetation. But in case of microwave, if the wavelength is sufficiently longer, it penetrates through the vegetation. Even if it is a close or dense forest, it can penetrate, and you can get this terrain image, the image of the terrain surface. So that is one of the very important advantage. Similarly, it can penetrate through ground. So many of the subsurface geological features, like your buried paleo channels, like Saraswati River, you know, this is a buried mostly. So for such applications, this your longer wavelength radar is very, very useful. Similarly, for active fault mapping also it is important, and other subsurface your civic structures like oil and water pipelines, like sewerage lines, and particularly in the city area. So this radar remote sensing is very, very useful. Okay, sometimes maybe this your satellite-based remote sensing is not very, very relevant because it can not penetrate for a longer this depth. But in such cases, you need to use the ground-based radar to get these your structures, underground structures to be mapped. And you see the next point, the side-looking imaging. It is highly sensitive to topographic elevation, and that is helpful to highlight the geological features like geological structures, like a fault, like a lineament. Also, it is very, very important to highlight these geomorphological features or the landforms. Now, there are disadvantages as well. And what are the disadvantages? There are some of the very, very prominent disadvantages is in case of radar, there are speckle noise is one of the major disadvantage. What is speckle noise? It is like a salt pepper effect. If you make salt and pepper together, then what do you find? You find white and dark, isn't it? Some granular appearance, granularity. So you will see the granularity on the image. The image is, this tone is not very, very uniform. Although this your land cover is same, although this land cover, for example, is only forest, but you are getting a lot of granularity. That is speckle noise. And why the speckle noise? We are discussing. And the next disadvantage is it has some geometric distortion and relief displacement. And this is very, very important in case of rugged terrain, where the terrain is reasonably flat or gentle topography, geometric distortion is very, very less, and it is not a serious problem. But in case of very rugged terrain, like in the Himalayan terrain or other mountainous terrain, so this geometric distortion is very, very strong. And the other disadvantage is radar, you see, it is not sensitive to color, and also this mineralogical composition. It is only sensitive to the electrical properties, rather the dielectric properties of the minerals, and some of the geophysical and geometrical properties of the surface, like the surface roughness, surface geometry, and the feature orientation. So these are important, but it is not sensitive to the color and composition, mineral composition, which is very, very important in case of optical remote sensing and hyperspectral remote sensing. You get the absorption spectra, and from this absorption spectra, you can identify a particular mineral, not only the rocks, but a specific mineral, a particular mineral you can identify. Here, it is not possible. You can only identify certain your broad rock types or some of the geological materials based on their geophysical properties, based on their dielectric properties, and their geometry of the Earth's surface. Now here this you can see one example of the speckle effect. On the left side, this is one optical image. Basically, it is a Landsat TM, this your false color composite image. I have converted to this black and white image, and this is the area is the Doon Valley, okay, and Dehradun is somewhere here. You see here is the Dehradun, but here it is not very prominent where exactly Dehradun is, but here you see this bright patch is Dehradun city. So here you see these are the areas is the Piedmont area, and these are the Shivaliks. This is the Jamuna Tier fault, this is the Ganga Tier fault, these are again Piedmont. They can here this is the rivers, Assan rivers and many other rivers. These local people can tell because you are from different parts of the country. It is difficult for you to know the individual river names like local these rivers, but you know this is the Jamuna Tier fault and this is the Ganga Tier fault, and the Jamuna river is flowing along this fault, and this is the Ganga river. This is the Shivalik formation, and again Shivalik is here coming here. After that there is the MBT, and this is the Himalayan terrain. Now you see here this land covers like Piedmont region. Okay, this is the Babar zone and this is the Tarai zone and the Shivaliks. The tone you see it is more or less uniform. But if you see here in this case, here there are a lot of granularity. Lot of granularity you can see here, isn't it? And why this is this granularity? That we'll explain, we'll discuss on that. But see, this is the difference between these two. Here the tone is uniform and it is very easy to interpret, but here a lot of differences in the tone. But at the same time, you can see the micro-topographic is highlighted. Topographic features are very much highlighted. You see the city is very bright because of from here the scattering is very high. Some of the things are very much important in the radar remote sensing, but some of the things it is very difficult to interpret because of the speckle effect. There another problem you can see here, the Himalayan terrain, the topography is upright. But here you see there are a lot of geometric distortion. At some places there are topographic reversal has also taken place. For example, these are the areas where the geometric distortion is very strong. These are the areas known as foreshortening. There are layover, there are foreshortening. So these are some of the geometric distortions. These terms we will discuss. Now see this speckle effect, why this speckle effect appears. So speckle effect in SAR image, it results from the difference in the vectorial sum of the backscattered energy from the elementary targets or scatterers in adjacent pixels. Here you see there are 4 pixels are given here. All the pixels have the similar elementary targets, similar scatterers, similar features are there within these pixels. You see, this is the by this color we have shown more or less similar features for this and for this. Isn't it? All are similar features, but at different positions. So their geometry is different. In fact, this is microgeometry or micro-topography is different. But radar is sensitive to centimeter because their wavelength is centimeter. So the micro-topographic differences can cause this return signal at different time. And from each pixel, there are hundreds of these return signal are coming back. These hundreds of return signal while coming back to the receiving antenna, they will interfere with each other. And this interference, sometimes it can happen constructively, additive one, the constructive addition, and sometimes it may be destructive addition, depending on the differences in the distance, okay? Depending on due to their differences in the micro-topography, this between the features. So in this case, for example, although the features are all similar or exactly the same, but in this case, because of these differences in the micro-topography, there is constructive addition. As constructive addition or constructive interference, the return signal vector is long. So here the strength of the return signal is stronger. So this particular pixel will appear brighter, whereas in the other case, this pixel where from return signals while coming back, they are interfering and there is a destructive addition is taking place. Essentially a destructive interference is taking place. Return signal vector is very short. So the final strength of the return signal is low and this pixel will dark, although these features are similar. But one pixel looks brighter, one pixel looks darker. So this is what is speckle effect. Although the features are same, for example, it may be forest, it may be agricultural land, it may be this similar kind of land cover, but due to these microtopographic differences of the scatterers or the elementary targets within the pixel, their return or your vectorial sum will be different due to the interference effect, and one pixel will appear bright, one pixel will appear less bright or darker, and that gives you the speckle effect. Okay? So speckle is the vectorial sum of your responses from the scatterers or elementary targets in a pixel, and for a layman, the speckle means what? It is a granular appearance on the image, or it is a salt paper effect. But for its scientific understanding, it is because of the differences in the interference of the return signals. And so interference is a function of the number of return signals, and number of return signal is a function of the number of scatterers exist in a pixel, number of elementary targets in a pixel, and number of elementary targets is defined by the wavelength of the radar. If the wavelength is long, the elementary targets, number of elementary targets will be less. If the wavelength is short, the number of scatterers or elementary targets will be more. Okay, so there is more scope of different kind of interference. If the number of elementary targets are more, that means if the wavelength is shorter. For longer wavelength, speckle effect is less. So what I mean to say that in case of longer wavelength, speckle effect is considerably less. In case of shorter wavelength, speckle effect is stronger. So this speckle effect or this granular appearance or this salt paper effect needs to be reduced. You cannot wholly remove it, you can reduce it. And there are a number of ways to reduce it or suppress it. A common method for the suppression of the speckle effect is multi-looking. So number of these looks can be combined together and we can take an average. So mean of different looks. The speckle reduction takes place as a reciprocal of the number of looks, 1 by n, how many looks you have combined together. And there are other ways without losing this resolution. In this case, while you do multi-looking, your resolution will be coarser than the original resolution, I mean spatial resolution. But there are other ways where without losing resolution, you can suppress this speckle effect. One of them is the spatial adaptive filtering. The number of adaptive filtering techniques are there. Okay, like there are the Lee filter, this Frost filter, then your map filter. There are many more, enhanced Lee, many more these adaptive filters are there. These filters can be used. And the other ways is the multi-date, this your data fusion, multi-date image fusion. Same time, multi-band data fusion is also possible, which can also reduce the speckle effect. Now, the other this problem in case of radar remote sensing is the geometric distortion. And what are the different types of geometric distortions are? Like there is foreshortening, there is layover, and there is shadow. What is foreshortening? If a topographic slope is directed towards the radar, or if a topographic slope is before, just listen carefully, if this topographic slope is before this radar, means if this topographic slope is towards this radar, then what will happen? This length of this topographic slope will be shortened. So when this topographic slope is before the radar or towards the radar loop direction, it gets shortened, and that is why the terminology comes foreshortening. Before the radar, it gets shortened, so it is foreshortening. And here you see layover, where it is reversal of the topography. That means the top of the hill is imaging first, and this foothill is imaged later. But on this image, like on the ground, we need to see first the foothill, and then we'll slowly we'll see this your slope of the hill, and then finally the top. But you see in this case what happens? You can see only it starts from the top of the hill, from the peak. There is no this your foothills. You can see the foothills of the other side only, but this side, this foothill is missing. Why? Because it images first the top of the hill. Why it happens? Because of this the distance of the top of the hill becomes shorter from the radar antenna than the foothills. Foothill distance is longer. Why it happens? Because of this topographic slope. When this topographic slope is larger than the radar look angle. There are other geometric distortions. Sometimes it may happen that the radar pulse does not reach the other side of the topographic slope. For example, here the radar loop direction from this. So here radar beam comes like this. But if the radar beam is not very steep, the radar beam is gentle, then what will happen? It cannot reach some of the areas on the opposite slopes, and it will remain dark. So these are known as the radar shadow. Now, like in optical remote sensing, we need to know this. What is the spatial resolution of the image? Then only we will come to know how we can resolve the targets. What is the size of the targets we can resolve? What is the distance we can resolve between two different targets? Okay, this is known as spatial resolution. You know that. In case of optical remote sensing, we only tell about one spatial resolution. For example, panchromatic image of this ResourceSat or Cartosat image of ResourceSat is 2.5 meter. What does that mean? It is a square pixel of 2.5 meter on both the sides, X side and Y side, azimuth sides and the range side. There is no range in case of optical remote sensing because it is nothing looking image. So in case of panchromatic image, it is 5.8 pan image. In case of LIS3, for example, it is 23.5 meter. LIS4, it is 5.6 meter. So these are all one value for the spatial resolution. But in case of radar, there are two values, two spatial resolutions. One is along the range direction. This is the dimension of the pixel, and another is along this azimuth or this orbit direction. This is the two. This you can see here. This range resolution is a function of the pulse width, and pulse width, you know, it is defined as the time. And this time can be multiplied with this speed of the electromagnetic radiation, that is the speed of light. Okay, so this is the range resolution is c tau by 2 along the radar beam direction. But we are interested to have the resolution on the ground. Then we need to consider this, what is the look angle of the radar. If the look angle is theta, then the range resolution on the ground direction, that is the ground resolution, is c tau by sine theta. The azimuth direction, this resolution is governed by different factors. The factors here are, see, this is azimuth resolution, k, psi, and this is r. Okay. So here psi is important. This is known as the angular aperture or view angle. Psi is basically the lambda by L, and r is the range. It is a function of the height of the satellite or the spacecraft or the aircraft. So this is h by cos theta, height of the platform, and the theta is the look angle, and h by cos theta, or r is range. But what is important is lambda by L. Lambda is the wavelength and L is the size of the antenna or length of the antenna. Wavelength of the radar is fixed, and height of the radar is also more or less fixed. It is fixed only. So what is important? This is the antenna size. So essentially the azimuth resolution is controlled by the antenna size. Okay, along with this also range as well as lambda, and k is the factor. So now you see here this L needs to be very, very long. Why? Because L is on the denominator. So longer the L, shorter is the RA, higher is this azimuth resolution. But you cannot have a very long antenna in space. It is difficult to fly with a very long this antenna. So that is the reason this azimuth resolution is very, very coarse, because we have limitation in its flying. For example, in case of a radar which is using a frequency of 10 gigahertz, that is equivalent to 3 centimeter wavelength, but the antenna size is 3 meter, pulse width is 0.5 microsecond, and the look angle is 45 degree. Okay, and if the range is around 10 kilometer, which is equivalent to around 7 to 8 kilometer height, okay, or it is 100 kilometer range. So you see what is the difference. In case of 10 kilometer, you get the azimuth resolution 80 meter and range resolution 106 meter. Okay, but while this height is increased and range is increased to 100 kilometer, azimuth resolution becomes 800 meter. And if this height or the range becomes 500 kilometer, which is the standard height of the satellite, 500 to 700 kilometer. So in that case, what will happen? It will be at least 4 kilometer is the azimuth resolution. But this kind of resolution is not suitable for our standard these mapping applications. See it? So that is why we need an antenna of very long size, but very long antenna we cannot place in space. We cannot fly. So for that, the concept of this, the aperture synthesis or synthetic aperture, synthetic antenna came into picture, and the synthetic antenna by Doppler principle was adopted. So here what happens? Instead of a very long antenna, we use a very short antenna, but moving. Instead of very long stationary antenna, it is equivalent to short and moving antenna. And it's a short moving antenna as it is moving along the orbit. The same target, white spot, can be imaged as this satellite is moving along the target at different distance, at different points on the orbit. It can image this target. See, this is the position when the distance from the antenna is the shortest, and this position is known as the Doppler centroid position. Again, as the satellite is moving along the orbit, this is the last point of the satellite, when it can image for the last time the target. So all along this distance of the satellite, all along this location of the satellite from this, as it moves up to this, okay. So this is a long, your distance on the orbit. The satellite is imaging the same target. So this long distance can be considered as the antenna if you can process all the images together in the laboratory, and that is this synthetic aperture radar. But in this case, we need to compensate the frequency with respect to the Doppler frequency, which is DC, and with respect to this time at the central position, that is the Doppler central position, TC. So this frequency compensation is required. If we do that, then we can get a focused SAR image, and where the resolution, azimuth resolution becomes few meters. So for a focused SAR, azimuth resolution becomes a few meters, and range resolution can be achieved to a great extent by reducing the pulse width, and when it is not possible to reduce the pulse width, by frequency modulation it can be reduced further. So by reducing pulse width and frequency modulation, range resolution can be obtained, this good resolution, and azimuth resolution by synthetic aperture radar concept. So what is the advantage of synthetic aperture radar? A small physical antenna can be used. But in case of real aperture radar, we need to place a very long antenna, which is difficult to manage. And in case of this synthetic aperture radar, particularly in case of focused synthetic aperture radar, the resolution is not dependent. It is independent of wavelength, range, and you know what is the best possible resolution, azimuth resolution? It is L by 2. L by 2 means if the antenna is very short, so it will be even shorter than that, L by 2, where the L is the length of the physical antenna. Now, you can see this radar backscattering or SAR backscattering. SAR backscattering is controlled by these parameters, like some are system parameters and some are terrain parameters. System parameters like wavelength or frequency, then what is the look angle or incidence angle as it is incident on the ground, and look angle when it is the radar beam is transmitted from the antenna with the perpendicular, the angle is look angle, and while it is incident on the ground with the perpendicular, this with the incident ray angle is the incidence angle, and then the polarization. So these are the three important factors. And there are some secondary factors like transmitting signal power and antenna gain. And what is more important for us is because system parameters are fixed by the system people. But what we need to interpret as a remote sensing geologist or as a earth scientist, we need to know what is the effect of dielectric property of the earth materials, what is the effect of surface roughness, terrain slope, and feature orientation. And finally, you get this backscatter radar energy or backscatter radar radiation, and this is known as the ratio is known as the synthetic aperture radar backscattering coefficient, or sigma naught, and it is equal to K into magnitude of received pulse divided by magnitude of transmitted pulse. In the linear scale, it is a quite wide range, so to make it narrower, we convert into decibel, and this is 10 log 10 of this sigma naught in linear scale. Now coming to the spectral bands in radar. So there are different spectral bands in radar, like K, which is 1 centimeter. Then this X band is 3 centimeter. Okay, you can see the satellite or spacecraft. In case of X band, there are many SRTM or XR. These are the spacecraft, TerraSAR X, Tandem X. These are German satellites. RISAT 2 is ISRO Indian satellite, Cosmos Skymet Italian satellite. Then in C band, 5.6 centimeter wavelength, the RadarSat Canadian satellite, ERS 1, 2, ERS 1 and 2, NBSat. Okay, then also RadarSat 1 and 2. Then again the spacecraft, SRTM spacecraft, then RISAT 1 or RISAT 1 of Indian satellite, Sentinel 1, again European Space Agency. Okay, so all the satellites use C band. So C band is very, very widely used. Then S band, which is 10 centimeter wavelength, is Almaz Russian satellite. Then your Chandrayaan 1 planetary missions, Indian Chandrayaan 1 mini-SAR, again Chandrayaan 2 dual frequency SAR. There is also S and L band. And this, in the coming year, there is a NASA ISRO synthetic aperture radar. This mission is going to be launched. So this is also using S band as well as L band. Again, in case of this L band, which is 23 centimeter wavelength, here these are the satellites and spacecraft. And in case of P band, because the wavelength is very long, around 70 centimeter, so this electronics is a little complex. It's more complex. All are complex electronics only in case of radar, and it is more complex. So P band, this your wavelength is used popularly in airborne sensors. But in case of satellite, is not yet, there is no satellite yet which uses P band radar, but it will be launched in the near future, maybe in the next year. European Space Agency is going to launch this mission biomass, longer wavelength radar. It will be very, very useful for biomass mapping of the forest area. That is why the mission name biomass. Now there are different SAR imaging modes, So like popularly used imaging mode is the strip map. The entire swath can be imaged. These are most of the satellite uses the strip map. But here there is a limitation of the swath size, but it goes up to 100 kilometers or so. There are ScanSAR, it is a wide swath. This your mode, like these are the satellite uses the wide swath, RadarSat, NBSat, RISAT 1, MRS, CRS. Okay, this is different beams are used. And Spotlight, it is a focused one, and here very high resolution applications are achieved by Spotlight mode. But essentially we use the strip map mode, most of the applications. In some cases we use the wide swath ScanSAR mode and also Spotlight mode. Now see, this is the SAR imaging modes by different these your missions. Like this is RadarSat missions. There are different imaging modes. For each imaging mode, these look angles are not same. So like strip map, like ScanSAR, okay. So these look angles are different between these imaging modes, as well as within the same imaging mode. The look angles can be different. You see, this can be look angle, this can be look angle, is different. Similarly, for NBSat, there are different look angles for different images is possible, different look angles. In case of Sentinel 1, where the data is presently available, freely downloadable data, Sentinel 1, here you see there are data available in case of strip map, and mostly it is available for the wide swath IW mode, interchromatic wide swath mode. Okay, but the look angles are different. Now, because of these different look angles, with this topographic slope, there are different kind of geometric distortion take place. Like layover takes place when the topographic slope is greater than the look angle, and foreshortening when the topographic slope is less than the look angle. Okay, and shadow when this radar beam is gentler, so that it does not reach on the other side. So this illustration is very, very useful. You can see here. Here you see this is the topographic slope. This topographic slope is greater than this look angle. Look angle, if you draw a perpendicular with this radar beam direction, this is the look angle. So this angle, which is alpha, is greater than this this Luke angle, this topographic slope is greater than this Luke angle. So what happens? This distance, the top of the hill, this distance becomes shorter than the foothill distance. You can see this. So that is why first imaging takes place from the top of the hill, then imaging takes place on the slope of the hill, at the end from the foothill, on the ground. So that is why there is topographic reversal or layover effect is taking place. As this topographic slope here in all the examples it's same, but this Luke angles becomes different. As the Luke angle becomes larger, then what happens? Here the layover is taking place, but this at the same time this slope is getting reduced in length. And in this case, you see, entire topographic slope becomes perpendicular to the radar beam. As it becomes perpendicular to the radar beam, what happens? The entire slope, entire topographic slope, entire segment appears as a single line here. You are missing this entire slope on the image. You get only a single line. So this is shortening of this image, this ground area on the image. Now here you see, when the Luke angle is larger than the topographic slope, or otherwise when the topographic slope is lesser than the Luke angle, then this slope becomes shortened. Okay, but there is this slope is upright, but here the slope is reversed. Now coming to the polarization. In this lecture we will discuss only on the linear polarization. You know this, you are transmitting this polarization can be either horizontal or vertical. Horizontal or vertical. So if it is horizontally transmitted, and after interacting with the Earth surface, it is return signal coming back. It can have horizontal, it can have vertical, and all intermediate your vibration directions. But the sensor will receive only the horizontal. If it so happen, then this polarization is known as HH, means horizontally transmitted, horizontally polarized signal is transmitted, and horizontally polarized signal is received. Other case, if the vertically polarized signal is transmitted and vertically polarized signal is received, then this is known as the VV polarized. And again, when it is, these are known as like polarized images, whereas VH and HV are the cross polarized, because you are sending vertical polarized, but after interacting with the Earth surface, it changes its polarization direction because of the ruggedness of the Earth surface. So then you are receiving H, so it becomes VH or HV. These are cross polarized images. Now you see the utility of these like and cross polarized images. This is for example is for the drainage or hydrological mapping. See here, this is in HH. This surface scattering is highlighted. So all the drainage, those are appeared on the surface, are very much detectable. But in case of VV, only the major drainage, where the topographic ruggedness is very strong. Major, your rivers with the banks have the elevation difference with the ground, then those channels are highlighted here and can be detected, can be mapped. In case of HV, cross polarization, this image, in this case what happens? It gives you the volume scattering. Volume scattering means it goes inside the volume and it comes back. So it has the ground penetration capability. HV or VH has ground penetration capability, whereas HH and VV, they are coming from the surface, and HV and VH, they are going inside the volume or volume scattering. That is why it can give you these near surface channels, when some of the channels which is covered by the boulders or gravels and not very much apparent on the surface, but there is a river bed which is wet and moist. So in such cases, this can be mapped. So near surface channels can be mapped. Okay, like here I have given one example. This is the Bay of Bengal area. This is this very important island, Sagar Island. Okay, so this is your Orissa region. This is the West Bengal region. Now you see this Bay of Bengal area. There are three images are given. One is HH, one is VV, and one is HV. Now, if you understand well this, what is the impact of the polarization, you will be able to identify which is HH, VV, and HV. So please study a little more. I'm just telling you. In this case, this is HV, because in case of HV, in case of water, there is no volume scattering is taking place. So that is why water appears dark and the land appears bright. So this is cross polarized image, and these two, one is HH, one is HV. VV. And here, in case of HH, there is the dielectric contrast or the material, this your moisture contrast or material, this contrast is highlighted. So that is, this is HH. And in case of VB, only the major topographic breaks or ruggedness is highlighted. So this is the VB. So this is HH, this is VB, and this is HB. Now coming to dielectric property, this is the electrical property of the matter, and the dielectric constant is defined by this K is E naught by E. This is the applied electrical field which is transmitted from the radar, and this is it goes inside the material volume. Okay, and EP is the polarized electrical field. And when the polarized electrical field will be significant, when there are sufficient moisture in the material or free H2O molecules. Free H2O molecules, because of its very, very interesting this your molecular this crystal structure. No, you know it is sp3 hybridization in case of H2O, sp3, but it is distorted these angles. No, this bond pair, and then lone pair, and bond pair, lone pair. This geometry gives you very, very distorted geometry or distorted tetrahedron, and because of that, as this radar pulse is reaching this any H2O molecules, it gets polarized. The signal gets polarized. So whenever there is free H2O molecules, radar pulse gets polarized. So EP will be substantial. Then the radar return will be high. So in case of water, in case of moist soil, so this your dielectric property is high. For example, in case of free water, dielectric property is 87.8. So the entire radar pulse will come back. Only 1 by 87.8. This is the fraction, 1 by 87.8, that is going inside the volume. Very, very negligible. So entire radar pulse is returned from the water bodies or moist soil. Whereas in case of these dry rocks, soils, in case of metals, it is little high. Okay, where the electrical these materials are there. In case of vacuum, it is 1. Okay, so the value can be 1 to highest value is around 87.8 or so. When the value is high, then this will happen like this. Because of high value, what will happen? It will return on your earth materials. Because of the high your dielectric property, means when the material is wet, the radar return will be high. Okay, like in this case, if you see, this is a lava flow. Okay, this is an optical image and this is a radar image. Lava flow is wet, so that is why in optical image it appears dark, whereas in case of radar image it looks bright. And you see here the speckle effect is very strong. No, here it is smooth image, but here speckle effect. But see the structure, geometry of your volcanic cones. This is your breached volcano. All this geometry of the volcanic landforms are very, very prominent, which is not so in case of optical image. Now radar, you see, it can penetrate through ground also, and the ground penetration is a function of what is the dielectric property of the material and the wavelength. If the wavelength is longer, then only it will penetrate more. But at the same time, the material should be favorable. How it should be favorable? Material should be dry enough. Material should not have high dielectric property. Dielectric constant should be low. So where dielectric constant or dielectric property is low, where the moisture is low, in case of desertic sand deposits, the dielectric property or moisture content is very, very low in arid region. Whereas in case of alluvium, in case of altered rocks, in case of hydrated rocks, like in case of boson, no, in case of sulfide deposits, you know, these boson you find on the surface. So these are all altered, these minerals, hydrated minerals. In such cases, your dielectric property is high, moisture content is high. So in such cases, this penetration will be less. But in case of desertic sand, penetration will be more. So, but at the same time, what is important? The wavelength. Wavelength should be long enough to penetrate, and loop angle should not be very, very gentle. Then in that case, this penetration will be low. But essentially, it is controlled by the dielectric property of the material and the wavelength of the radar. Now coming to your surface roughness property. The surface can be either smooth, it can be rough, or it can be anything in between the smooth and rough surface. Okay, but the concept of roughness, surface roughness, is a function. It is relative. The same surface can be smooth, or if the wavelength is very long, but it can be rough if the wavelength is very short. So there are two factors are very, very important. One is what is the height difference, the top enveloping surface and the bottom enveloping surface. That is the definition of the surface roughness. And what is the wavelength? Okay, so the relation between this wavelength and the radar wavelength and this delta H, or the surface roughness, is this your enveloping surface to tangential surface. What is the height difference? That is decided by the Rayleigh's criteria. So smooth surface reflect all the energy away from the antenna, because smooth surface will act like a specular reflector, whereas rough surface will act like this diffuse this scatterer, isn't it? So because it scatters diffusely, so energy will be radiated back in all the directions, irrespective of this direction of the transmitting your radar beam. In case of intermediate surface, scattering is taking place in all the directions, but there is one component, one good component is specularly reflected in a particular direction. So that is why in a particular direction radar return will be more, but this return signal will come in all the directions as well. So it is also Lambertian. Okay. Now you see this, for example, here when the river is come around the year, river is not very turbulent. It is mostly come river water, but during the rainy time it is very turbulent. There may be flood as well. So during this year come period, river looks dark, because river surface, although dielectric property is very, very high, but the radar return does not take place towards your antenna, because you have the receiving antenna at the same place where the transmitting antenna is. So transmitting antenna, receiving antenna at the same place. It is transmitted, then it is going back. Like this illustration you can see, this is an aircraft. It is transmitted and it goes back, goes in other direction. It does not come back. This where the receiving antenna is located. It does not come back here. So that is why what it happens, that you cannot receive any signal and this target appears dark. But when the surface is very, very rough, when it is a very turbulent one, then what happens? It acts as a Lambertian surface, like a diffuse scatterer. So in all the directions scattering will take place. So substantial amount of this radar return will come back to this receiving antenna. That is why it appears bright. Now the orientation of these geological features or the linear features are very, very important. If the orientation is along the direction of the radar beam, it is very difficult to highlight the feature or detect these features. Okay, it may be possible, but it is difficult. But if the feature is oriented perpendicular to the loop direction, then what happens? A lot of return takes place. Like this is one geometry you can see. This is the ground. This is a building wall. This is a big building wall. This is the roof. Now what happens if the radar pulse is incident on the ground? Then it will be reflected like this. Again, it will be reflected like this. Here with the perpendicular, the angle of incidence will be angle of reflection. Here also angle of incidence will be angle of reflection. But because of the geometry of the target, this almost the entire energy or the major part of the return energy coming back to the antenna. And this geometry is a dihedral geometry. Two surfaces perpendicular to each other. It gives high radar return. So like in case of buildings, in case of bridges, in case of settlements, in case of urban area, so this kind of objects you can see. So in a city, because of these dihedral objects, which is also known as a corner reflector, so this area will look very, very bright. So this is due to corner reflection. Like you see the images here, this is one of the image of the Shillong plateau. So here the radar beam is coming from this side. This is the radar loop direction, and this slope looks bright, whereas this slope there are the radar shadow. There are a lot of these geometric distortions. Some are layover. Okay, some are foreshortening. Okay, so this you can see geometric distortion as well. But here you see this is this Kolkata, this city, and this is your continental, your land area, where the agricultural lands are dominantly covering this area. So it looks dark, whereas in case of mangrove, the profuse vegetation as well as this mud flat, so it is wet as well as lot of water in this vegetation, so that gives you bright signature. Okay. And here is the city, because of the dihedral objects, buildings, it gives you bright signature. Now coming to some of the prominent geological applications, we will not discuss many, only a few. Like you see, but what are the advantages of radar remote sensing for geological study? First is, it is very sensitive to surface geometry. So it's high sensitivity to surface geometry. It provides information on geomorphology and geological structures. It's high sensitivity to surface roughness. It gives you information about these bare rocks, particularly in non-vegetated areas. Rock type mapping is possible, broad mapping, and its sensitivity to moisture content or dielectric property. It gives you information on the unconsolidated materials, alluvium, and soil. And also for hydrated these mineral assemblages or these altered rocks. Again, its capability to penetrate through vegetation and ground, it allows to image vegetation covered terrain. In a forested area, you can get the terrain map, terrain image. And subsurface geological features like buried channels, like active faults in alluvial terrain, okay, that can be identified. If they are near surface, if they are not very deep, then only it can be identified. Now some of the examples you can see. This is a very general applications, but there are geological features also. Here you see the agricultural features like your circular pivotal irrigation. Some are wet, some are dry. Wet appears as bright and dry appears as dark. Again, rectangular plots also, due to the different types of irrigation, different stage of irrigation. One is wet, one is dry, one is there is crop, one there is no crop. It is a prepared field. One is just barren land, means it is just just vegetation, your crop has been cut. Okay, so those have different kind of signatures. But geological features, you see, their drainage are very much prominent. Bright lines it appears. Similarly, you see there are the structural ridges. You can very clearly identify. Okay, so sedimentary rocks you can identify because of the layered your appearance. So these are the broad applications, but here you see this rock types mapping is very much possible in this example, because here the rocks are exposed and their vegetation is not there. Okay, this is the sample from the Canada. So here the vegetation is very less, and this is there are the limestone, which is very hard and compact, so surface is very rough, so radar return is very high. There are sandstone and siltstone and shale. Okay, so see, in case of limestone, because of very high surface roughness, the radar return is very high and it looks bright. Whereas in case of sandstone and the siltstone, sandstone is intermediate grain size, isn't it? The grain size is how much? 2 to 1 by 16 millimeter, isn't it? So sandstone and then silt, or this shale or siltstone rocks, which is finer than 1 by 16 millimeter grain size. So because of the finer grain size, it gives you smooth surface, and so the radar return is less and it appears darker, whereas the sandstone appears brighter. So this is the map you can see: limestone, sandstone, okay, then siltstone or this claystone. So all kinds of rocks can be mapped very nicely based on the surface roughness properties. Now you see, if we can use radar image in addition to optical image together, so it is a fused product of your optical multispectral image and a radar image. So there is this beauty of fusion of all these optical image and radar image, because in optical image you have the spectral information which is sensitive to the color and composition of the materials, whereas because of radar it is sensitive to the surface roughness, surface geometry, and it can penetrate subsurface. So there are a number of features in optical image you will not find, but it is very much prominent in the fused image. Like you see, for example, it is a very general one. The structural hills are much prominent here because the radar highlights these structural hills or structural ridges. But most importantly, you see this buried channel here. The buried channel in optical image, this is not visible, but it is because radar is fused, so it is very clearly it can be seen here. Similarly, this is an impact crater. Impact crater boundary is very prominent. But most importantly, you see this is the area These are sand deposits. Okay, and this topography is very gentle or more or less flat, but you see there are some long, these linear features. What are they? There are the dunes. In fact, they are the longitudinal dunes. So longitudinal dunes are very much prominent because this radar image highlights the geometric properties of the surface roughness property. So that is why these dunes are getting highlighted. In optical image, you will see only a uniform your color, but in this case, your dunes are also highlighted in this sand deposit. Okay, this arid plain. Now for lineament mapping also, it is very important. But see, in case of optical image, some of the lineaments can be mapped, but in case of radar image, it highlights these lineaments. Those are expressed through the topographic elevation differences. And there are a lot of possibilities. You can have image during the ascending orbit or ascending node. You can have image during descending node. For example, it is descending node when the satellite is coming down, and this ascending node when the satellite is going up. There are different look angles are possible, different polarizations are possible. So you are just two example, you see two images, one is descending, one ascending, and see that the features are highlighted a lot, because in descending there are some, these lineaments are highlighted, and in case of descending some other set of lineaments are highlighted. See, in this case this set is highlighted. In this case, along with this set, there are one more set is highlighted here. Okay, and this is the optical, is your angular distribution or Rose diagram of the lineaments. Now for mineral exploration, it is, for some of the minerals it is very useful, although you understand that hyperspectral remote sensing has very high potential for mineral mapping and mineral targeting for mineral exploration. Particularly for superficial mineral deposits, hyperspectral remote sensing is very useful. There is no doubt about that. But here some of the mineral deposits where these structural features are very important. Okay, like hydrothermal mineral deposits, those are like this accumulated like lodes or veins, and here the structures, geological structures like your faults, like lineaments, like shear zones are very important. So here you see, if we interpret from radar data alone, we can interpret many of the faults, many of the lineaments, means joints or fractures, and the shear zone. These are the potential areas where the mineral can be accumulated. Mineral deposits can be prospected, those areas. But if we combine these two, then the information content is more than double. So we can highlight, these are the areas where the mineral deposits potential is very high. Some of the areas here where this fault and these fractures, intersections are there, as well as these your surface signatures and the spectral signatures are also supporting this mineral deposit accumulation of the minerals, and in terms of the spectral absorption properties. So based on that, this mineral targeting or mineral exploration can be done very efficiently. You can use both these hyperspectral as well as your microwave remote sensing data. Now coming to RISAT or RISAT image, so just for Indian examples, so you see this is in the RISAT there are different imaging modes. There are fine imaging modes, there are this fine resolution FRS 1 and 2, medium resolution MRS, and coarse resolution imaging modes. Fine resolution is strip map, and MRS and CRS they are scanner mode. These are this resolution along the slant range, okay, from 3 meter to 50 meter, and these are the swath. What the image I will show, that is the MRS 25 meter resolution, and 115 kilometer, 115 kilometer is the your swath. These are the different parameters of these imaging parameters of the FRS 1, 2, and MRS and CRS images. Now see an example. We have HH and HV image of the area, that is basically the mining area. We have taken a number of images, but the purpose is multi-temporal averaging, so that speckle effect can be reduced to bare minimum. For that purpose, we do adaptive filtering first, then multi-temporal averaging we have done, then some filtering we have done, and we have subset as per our study area. Then you see in HH image, this is the image looks great. But if we see some of the segments, some of the parts of these images, see, for example, if you see this part in HH, horizontal polarized image, it basically highlights the surface scattering. So the features, those are prominent at the surface, will be highlighted. Like your settlements, this is the city, Then like overburden dumps, like queries. So these are the things are highlighted here as a bright and dark spots. Okay, these are the areas. But here there is no prominent feature we can see here, isn't it? Maybe there are some very faint signature is there, but in case of HB, see surface signature are not so prominent. In fact, it is very, very subdued. But you see the near surface of subsurface signature is very much highlighted. Here this area is completely modified by agricultural practices and other land use practices. So no information is available, no signatures available about the geological structures. But because this HB gives you the subsurface information, volume scattering, see this information. What is that? It is a fault. This fault from near surface signature, it can be mapped. Okay. Similarly, this is another example, very interesting. See, this is one of the area. This is the part, okay, in HH and HB. See, in case of HH, surface scattering features are very much highlighted, like the settlement or houses, like overburden dumps and many more things, including this bridge through which you can cross this river. This is Damodar River, and you can cross this river because there is well-defined bridge is here. But if you do not see the HH image, if you see only the HB image, then there is a problem because it is a cross-polarization image. It does not give you the surface scattering information. And bridge is a dihedral object. It's a corner reflector. So here corner reflection is highlighted. But in HB, surface scattering is not highlighted. What you get, it is the volume scattering. This radar, this pulse is going inside the volume and it comes back. That is what you receive. It's not the surface scattering, and that is the reason the bridge is not seen. But both the images are acquired at the same time. In one case, you can see the bridge. Another case, you don't see the bridge. So that is what is your uniqueness of different polarizations. One polarization gives you certain features, another polarization gives you certain other features. In this case, you'll get the geological structures. You can get some subsurface features, and including the quarries are very, very prominent, okay, or open cast mining areas. So there are many more examples, but we stop here, and tomorrow maybe we will discuss on this SAR data processing, but essentially on the interferometric SAR and polarimetric SAR techniques, and there are these data processing techniques, the principles and applications. With this, I conclude today.